So we know that PFK is the rate controlling enzyme of glycolysis. What we're going to do with this slide is look at and explain some data that allows us to understand how that is done. Okay, so anytime we see a plot, remember we want to look at our axes, so let's look at what we have here. We've got phosphofructokinase activity, so that's PFK enzyme activity. And so really we're looking at V0. And then we've got fructose 6-phosphate concentration on the x-axis. So that represents our substrate concentration. So these are the typical kinetics plots that we'd see. We'd look at how the speed of a reaction is dependent on the substrate concentration. And with all of these lines, and we'll explain them all in just a minute, regardless of which one you're looking at, we can see that as we increase the concentration of substrate, we can see that the reaction gets faster. Now, one of the things we'll comment on is that some of these reactions or some of these lines are shifted more to the right than others. So we're going to get to that in just a minute. So let's go ahead and try to explain some of the conditions that we have here. One line that I want to kind of label that's not well labeled on here is what this dotted line is. And this dotted line represents physiological concentrations of F6P. So where do we tend to see F6P concentrations physiologically? So let's take these lines one at a time and see if we can rationalize and make sense of what we see. So taking that blue line first, this really represents normal conditions. And under normal conditions, we can see that when there's no substrate around, we've got no enzyme activity. But as we increase and approach physiological concentrations of our substrate, we can see that we get pretty high, near to full activity of our enzyme. So again, no inhibitors, low concentration sort of ATP. We see sort of this typical normal response for PFK. Now, we talked about on a previous slide the fact that we know that ATP is a potent inhibitor of PFK. Okay, we're going to see why in just a little bit, okay? But ATP is going to inhibit. So that's going to be our green line. So if we look at what we have here, our green line represents the addition, or not low concentration of ATP, but 1 millimolar concentration of ATP. So just, 1 millimolar concentration of ATP is enough to sufficiently inhibit PFK. So let's kind of label this here, and then we'll look at this graph again. So then when we add 1 millimolar ATP, we are going to inhibit PFK. Remember, when we see this symbol that represents sort of an inhibitor, okay? So it doesn't inhibit it so that it stops, but what it's going to do is sufficiently decrease the activity. So I'm going to spend some time here looking at this vertical line here, right? Because that represents physiological concentrations of F6P. So if we maintain that physiological concentration of our substrate, what we can see is that we take the activity from near to maximum down near to zero just by adding in ATP. So ATP is a very potent inhibitor of PFK. Now, the last line that we're going to look at here is the red line. So the red line represents when we add in just a little bit of AMP. So they're going to add in 0.1 molar AMP. And all of a sudden now we rescue a good bit of our PFK activity. Okay, and I should have mentioned this before looking at the green line, okay? What we really have, I'm actually going to move this down here so we can label this in here. What we have with our green curve, when we have inhibition of enzyme activity, we are going to shift the curve to the right. Okay, so that's a hallmark when you're looking at an enzyme activity plot. V0 versus substrate concentration. If we've shifted a curve to the right, that means we have inhibited the enzyme. We've made it slower. Okay, so shift curve to the right, we've got a slower reaction. Okay, so we can sort of see that. Now, we're going to do a horizontal line in just a minute to explain that, but let me finish up here with our red line here. So again, we can move that curve more back to the left here when we add in 1 millimolar ATP. Okay, so ATP or AMP, AMP is going to shift that curve back to the left, even in the presence of ATP. So even when we have that inhibitor present, just a little bit of AMP is enough to rescue that activity. So that indicates that AMP is a pretty potent activator. So AMP is a potent activator. So the last thing I want to put on here, and we did this a lot when we looked at plots, let's look at drawing a horizontal line. And importantly, we often draw our horizontal lines halfway up, okay? So this orange dotted line represents a 50% activity line. And remember, when we talk about what 1/2 Vmax is. So Vmax is the top of the graph. If I've drawn halfway here, this represents 1/2 Vmax. Okay, and 1/2 Vmax is equal to our Km. Okay, that is the substrate concentration that we have in order to have 1/2 maximal activity. Okay, so let's make sure we kind of put this in these words into what we see on this picture. So what this really means is if I'm looking at this halfway point, right, this is the Km under no inhibition. When I add in an inhibitor, if I want to get to the same 50% activity, I'd have to have a significantly higher concentration of my substrate. Okay, so again, shifting the Km to a higher value means I have to have more substrate in order to have the same level of activity. So we see that with our horizontal line as we change the Km value for that enzyme. Remember, that's going to be a Km apparent, right? And then looking at our vertical line here, that shows us if we maintain that same concentration of substrate, what we really do is we take an enzyme reaction that was fairly fast and we significantly slow it down. So the last little piece here, just to highlight, because this is something we're going to see again as we go through the course, is looking at molecules of ATP and AMP. I always want you to think about ATP as being an important fed state signal. And then AMP being an important need state signal. But one important thing I want to highlight here is the changes that we see in these concentrations are very different, okay? What we tend to see, change colors here, what we tend to see with ATP is only going to change plus or minus about 10%. Okay, so we really don't see significant changes in ATP. Well, why is that important? That kind of means that we're not going to be able to use it as a potent signal necessarily for kind of looking at what's happening in terms of need state versus fed state. However, when we look at AMP, okay, this changes, okay, plus or minus up to 400%. So we can basically have a 4-fold swing of AMP concentrations. And we'll talk about the enzymes that are responsible for doing that a little bit later. But the fact that we can have these significant changes allows us to identify AMP as being something that's going to be a shout in terms of, you know, telling us about our sort of system and the state that we're in, where ATP is really more of a whisper. Okay? So PFK activity is regulated by AMP and ATP levels. We're going to see how that plays in another video here when we look at the structure of PFK and understand how it's regulated. But it is important to understand that even though ATP can be a potent inhibitor, by having those changes in concentration of ATP be very minimal, we really rely often more on AMP changes to be a potent signal for what's changing metabolically in our system.